Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 8th, 2025, just 3 days ago. Alright, so this paper introduces a new method that allows a diffusion model trained on a single image to actually outperform one trained on multiple images. The paper is titled T-LoRA, Single Image Diffusion Model Customization Without Overfitting, and the visual comparisons really show how much of a difference their technique makes. The authors tackle overfitting and diffusion models by dynamically adjusting the training process based on the diffusion time step. Also, the authors shared their official implementation on GitHub. If you check it out, you'll find everything needed to get started, including detailed setup instructions, scripts for training and inference, and even a sample dog concept to test it yourself. It looks very well documented and ready to go. Alright, and this first figure really shows the practical difference. It compares their T-LoRA method to standard LoRA. Now LoRA, which stands for low rank adaptation, is a popular technique for efficiently fine-tuning a model on a new concept, but with just one training image, standard LoRA often overfits. You can see this in the bottom row. The model learns the cat, but it's stuck in the same pose every time. In contrast, the top row shows T-LoRA completely avoids this, creating flexible images of the same cat riding a bike or in a space helmet, perfectly matching the prompt. So how does T-LoRA actually achieve this improved flexibility? Well, this next figure breaks down the architectural differences. On the left, you have standard LoRA. A small, trainable adapter, marked with a fire icon, is added to the main frozen model. The key innovation, shown in the middle with vanilla T-LoRA, is that the rank of this adapter, which you can think of as its learning capacity, changes dynamically with the diffusion time step. Finally, the full T-LoRA on the right improves this further with a special initialization using singular value decomposition, which is a mathematical way to decompose a matrix into its core components, ensuring the rank is controlled more effectively. Moving to the results, this table provides the hard numbers. It compares standard LoRA against the two new methods, vanilla T-LoRA and the full T-LoRA. They're evaluated on two key metrics. First is image similarity, which checks if the generated object looks like the original. And second is text similarity, which measures how well the image follows the new text prompt. You can see that while all methods have great image similarity, T-LoRA consistently scores much higher on text similarity. This shows it's better at avoiding overfitting and creating flexible, diverse images. This table then broadens the comparison to other lightweight fine-tuning methods. We see T-LoRA 64 benchmarked against models like OFT and GSoft. Looking at the scores, the image similarity is consistently high and very close across the board, meaning all these methods are great at reproducing the object. But the key difference is again in that text similarity row. T-LoRA scores a 0.256, which is clearly higher than LoRA, OFT, and GSoft. This result reinforces that the new method strikes a superior balance, maintaining fidelity while allowing much more creative freedom. So to wrap up, what we've seen is that T-LoRA provides a really clever solution to a common problem. By dynamically changing its learning capacity across different diffusion time steps, it avoids the overfitting that plagues standard methods when you only have one training image. This leads to that superior balance we saw in the results. Excellent object fidelity combined with much greater creative freedom to follow new prompts. It's a powerful framework for data-limited content creation. That's all for this week's AI Research Roundup. Thanks for tuning in.